accepted. And now, without further ado, I will welcome our first expert of today, Salvador Venegas. He is a virtual attendee. He's a professor here at the Tecnológico de Monterrey. He was not able to come, but since we have virtual services and a good service that our colleagues are giving us, and he's going to be teaching us cybersecurity and quantic computing. Good morning, Salvador. How are you? I am looking at you in the screen. I can see you. Hi, good morning. And in case you want to share a presentation, great. Thanks so much. Here we have virtual and in-person interns. We have simultaneous interpretation. And that's it. All yours. Welcome. Thanks for being with us. I would like to first of all apologize for not being there. Uh, um, I have force majeure reasons for not to be there. And I am here to share with you some of the things that I've done in recent years about quantic computing. Here we have my contact information, and S. Venegas at tech.mx. I would like to thank the organizers and the staff of SSIG and Mr. Kuche, who is the one who originally contacted me to be with you. And thank you all. Thank you all for this invitation. I also would like to thank Tecnológico de Monterrey, the institution I've been working for many years, and thanks to the institute and thanks to all the scientific, thanks to it, many of the research, scientific research, it's a reality. Before speaking about quantic computing, I will tell you why I will be speaking about quantic computing. And I studied, before you were even born, I studied at the Tech in the state of Mexico, electronic systems, and then I went to Oxford University and I did an AI master's and a PhD in physics and in quantum computing, and then I came back to Mexico to work with tech. And then in 2008, I was a professor at Harvard University, also doing quantum computing. My group founded quantum computing in Mexico, and we've been doing several research areas. I believe it would be good to ask what is quantum computing. And the answer is that there are several answers to begin with. It depends who you ask to. Um, um, Fundaments of physics, what they are trying to find is a zone of test to tell if a specific versions and interpretations of quantum computing is correct. But for someone who is interested in building algorithms, computing is a multidisciplinary field where we have physics, mathematics, computing sciences, and others which are focused on the development of computers and algorithms. All of that are based on the properties of quantum mechanics. It is important to highlight this because the rules with which many of the systems we use work, public transport systems, digital television, the automobiles we drive, all of that will have the substrate that is going to be the set of laws that in physics we call the laws of classic physics, electromagnetism, mechanics, etc. And then those rules will typically translate into mathematical expressions. In the case of quantum physics, the same happens. If we study the aim of the quantum physics, the aim is to study very tiny things, like an atom, the hydrogen atom, for example, example, or those particles which are an atom. Also, in that set of objects we study, we have photons. Something very, very important to say here is that the mathematics that describe that world, the world of quantum physics, are very different from the ones we use in other branches of physics. Why is it like that? No one knows, but in the case of quantum, and those who are experts in this topic, apart from learning the maths which are needed in order to do digital computing, it is important and fundamental to learn the mathematics needed in order to describe and to predict the behavior of quantum systems in order to use them as computing resources. And it is one of the aims of the quantum computing to think in physics not only as physics but also the objects we describe as resources, as elements we can use. Now, this is with respect to quantum physics. Now, with respect to computing science, as many of you know, computing science is divided into three: computing, automatics, and complexity. The aim of these three branches is to describe mathematical models of computers based on those mathematical models and to identify and to characterize which are the problems that can be resolved with some mathematical constructs and what cannot be resolved, and if it is possible to have an algorithm, we need to tell how long it would take us to execute those algorithms. For example, the multiplication of matrix. I apologize. He needs to change her slide, I believe. Thanks. For example, the multiplication of matrix. It is one of the first ones studied in engineering degrees. There are several ways to multiply the matrix. The result should be the same, but the method will not necessarily be the same. So in this area, there are dozens of algorithms that multiply the matrix, and the aim always is to find a new algorithm that is going to be kind of faster than the previous ones. It will not necessarily be exponential accelerations or algorithms that will be a breakthrough in discipline. Sometimes a tiny improvement is needed for things to work even better. Another good example of this is the multiplication of numbers 3 times 5, 17 times 32.9. We would say the multiplication of numbers is the first thing we did when we built the first digital computers. How come there are people still doing research on how to make number multiplication even more effective? And the answer is yes. Yes, because the platforms we use today in order to make calculations are going to be very different from the machines we had several decades ago. The computers we use today are like the laptop that I am using, or mobile devices that will have a very important concentration of transistors where we want to use sophisticated algorithms, for example, facial recognition algorithms, medical applications. So the need to reduce, we need in order to improve the algorithm is very important, and this is one of the promises of quantum computing. This chart shows the performance of algorithms as time goes by and the polynomial algorithms exponential 2 to the 9, and there are factorial algorithms, and the aim of those is that for the problems we have, for the problems for which we have factorial algorithms, we can work with GPUs, quantum computers, and lots of creativity algorithms to reduce the time needed to implement this type of process. In science and in contemporary engineering, the problems we face when we're trying to simulate digital computers, we will find all these scenarios, and the algorithms we use consume lots of energy, lots of energy. So quantum computing is an area that is promising promising more or less effective and efficient solutions depending on how we address the problem. Quantum computing is transitioning. It's been several years of transition, and it is going from the scientific research labs to the industry. And for example, how branches of quantum computing are going to other disciplines, AI, and I believe this is the most important boom of quantum computing in recent years. If you have ever listened to statements, if you have read news about companies such as IQ and Sandbox and many others, the focal point, and even NVIDIA in the last Congress, it was one of the most important points. So the idea is to identify how to combine these hybrid spaces of quantum computers with advanced digital technologies to work in the intersection of AI, machine learning, and quantum computing, computational geometry, image processing, and many other areas. Now, apart from this, a scope of the quantum computers in other disciplines, we also have an ecosystem, which is the financial ecosystem, commercialization, and investment in order to produce objects and to produce specific devices that will be working on quantum computing. Investors, global companies, small to big companies, governments. There is a whole ecosystem, and the aim of this ecosystem is to make the wonderful things we have found in labs and in the theoretical work of the quantum computing is going to turn into products and services that will benefit mankind. This is the most technical aspect, and there are not that many mathematics. I just want you to see why quantum computers are different from digital computers. When I say different, I mean two different things. Mathematics that describe this type of computers, the quantum computers, and also how these computers can interact amongst themselves and with digital computers. A bit, as you might remember, is an element that is one element of one space to be scaled up with two elements, 0, 1, on, off, up, down. But regardless of how a bit is built, for example, if we use transistors, or as my grandfather used to say, he was a radio technician. They were using this type of relay devices to turn it on and off. The idea is the same idea behind a bit. And regardless of how we build this, the mathematical structure of a bit is always the same: one element in one space to be scaled up with two elements with the labels 0, 1, up, down, whatever. And in the case of quantum computing, quantum computers, to begin with, the basic processing unit of this discipline is qubit. You will find this as a qubit, CUBIT. These are different ways to speak the same. Cubic is the short term for quantum bit, and the big difference between the traditional bits or the digital bits and the qubits is that qubits are vectors. And this is a note that I wanted to share with you. In the junior high school, we learned that vectors indicated by a variable and then an arrow. And how this describe exactly the same in quantum computing is this bar. It is one as greater than, and then the variable in the middle. This way to describe vectors is very convenient when you are doing research work, professional computing, quantum computing work. It was created by an English physics, Paul Dirac. He was a physics Nobel winner during the first years of the 20th century, and it is very convenient. This is why I introduce it here. And this is the mathematical render, the formal introduction to the society of what is a qubit. A qubit is a vector that is defined in a 2D space, and it is also built on the base of the complexity. And this is the geographical representation of a qubit. And I don't want you to learn the mathematical structure of a qubit, but I want you to see that a qubit, one qubit has mathematical richness that the bits do not have. They have a more complex mathematical structure, and it is one of the very important points of the work of a scientist or an engineer working in this area to identify how to manipulate these parameters, for example, the theta or the phi parameters we have here, in order to make more effective and efficient calculations. Now, for this is the base. This is the base. These are the elements like the building blocks and the foundation of the building of quantic computing. And we need to have quantic algorithms. And quantic algorithms, I will introduce them now. But before that, I want you to think about the nature of algorithms. Look, to start with, when we first build an algorithm, the first thing we need in a digital computer, the first thing we need is to make sure the algorithm is doing what it is expected to do. And as Jan Ryu would say in one of his most recent books about computing and AI, he says an algorithm is like a recipe, and what matters the most about the recipe is that I want to have a good cake, because if not, the algorithm will not be good. Here, the same, we need an algorithm, which is a set of steps that is expected to produce the expected result. Now, once we have this algorithm, the next question, and this is once we have proven that this is the aim and that there is an algorithm, then the next question is, can we have other algorithms that will be better? And it would, I mean, to make them faster and to something that we could use to resolve the same problem. And here, faster means two different things. On the one hand, to use the computing resources we have access to. For example, if we have an old computer, I don't want to say Pentium because it would be like a museum. But if we have a sequential processing computer, I enter data to the CPU and it will be a processing with a tail. And this is, I can use the hardware the way it is, and that would be it. But what if instead of having this type of hardware, I have a modern computer with several pipelines, which is a multi-core, and consequently, I can do parallel programming with that machine, on that machine. If this is the case, what we expect from a competent programmer is to use, and that person will be using the parallelism resources of the machine. And when a problem is to be solved, it will be reasonably resolved. Look, here, this need to understand how the hardware works, the hardware of a computer, to use it to build fast algorithms. This is the focal point of quantum computing. It was the focal point of the quantum computing from the 90s and the previous century to the last 10 years, more or less, with the production of the first quantum algorithms. And quantum computing was born at the end of the 70s, last century, and it was a theoretical structure trying to understand theoretical physics. And this is when we start to see the story. So going back to this slide, remember, one way to quickly defining computing is to use the characteristics of the hardware you use to run algorithms. And as quantum computing is something very, very new, we need to understand how to use the physics of those systems in order to use them as computing resources. Now, another way to define, to quickly define or faster in computer is the design of algorithms, algorithmic strategies or meta algorithms to resolve certain types of problems. If you remember the problem of the traveling agent, it is easy to describe. The analogy is that Traveling agents will need to visit different places and they will have to pay for the trip. And one of the aims of the traveling agents is to pay a minimum cost because we do not know if you're going to be selling what you're expecting to sell, but you know that you will need to pay for the toll and for the buses. So if we abstract this work of the traveling agent and if we think in terms of each city they have to visit like a node and then we think about the roads. We're looking for an algorithm that would allow me to visit all the nodes and then go back to the original node because, for example, one person lives in Monterrey and the person wants to go back to Monterrey, so going and coming back to the same point, and in that round trip, we want to pay the minimum cost. This is the problem of optimization, and for this there is a solution, which is to list all the possible trajectories that will be found. But the problem is that doing this brute force work requires an algorithm that requires a factorial time. It is not a good idea because I will never finish and I will not have the possibility to execute the algorithm. But if I use a more sophisticated strategy like the healthy car algorithm, I will have only one algorithm that is going to be less expensive. It is not a polynomial algorithm, but it is going to be a more economical algorithm than the brute force. And this one, the healthy car, will have three very well-renowned names. So what do we need? What do I mean? We need to work based on creativity, the knowledge of mathematics, etc., in order to design faster algorithms in the digital world as well as in the world of quantum computing. Now, this is something that I wanted to share with you. How do we build a quantum algorithm? There are several ways. The most popular one is this one. And here I have a parallel on how we build a digital circuit. Here we have a digital, easy to describe circuit and non, etc. And then we have the exit. Now, what is the mathematical instrument we use in order to know which are going to be the transformations of the bit values of bits through gates? Well, it is going to be the tables of truth. For example, for the AND gate, any combination except 1 1, these are the inlet values, and we will have 0. So this is how we can predict how combination circuit is going to behave, like this one. In the case of quantum computers, we also have gates. Here we have the qubits, and those qubits are going to go through different gateways, and then at the end we will be able to measure, we will be able to retrieve information from these algorithms. Now, the big difference there is between the digital circuits, like the one we have in the lower portion of the slide, and the quantum circuits, is the fact that mathematics that describes quantum circuits is a more sophisticated mathematics, like the one we use in the digital circuits. In essence, how these types of circuits are described is by using linear devices. I am telling you this because my understanding is that there is an important number of students in the audience, and the invitation is to understand this mathematics. It is not that difficult to learn. It takes time, but you can quickly learn it so that we can understand how the quantum algorithms work. And if you want to start to do some research on this topic. And this is what I just presented, the mathematical description of a digital circuit. It is basically determined by the laws of the mathematical logic, and for quantic circuits, we need the mathematics that describes a quantic system, which is the linear algebra. There are other ways to do quantic computing, and here it will go beyond the education of an engineer. For example, this one here, examples of quantic computers which are available today. Not available to everyone, but to do research and to do sophisticated applications. The web company it has a set of quantic computers, and the performance is based on this differential equation. And for physics here, know it, it is a Schrödinger equation. And for those who do not know it, it is a differential partial equation. It can be first order or ordinary, but what matters most is not to see the mathematical properties of this Schrödinger, but there are different ways of doing quantic computing, and there is a mathematics that differs. Something important to say here is that nonetheless we're speaking about different mathematics, the ones of circuits and the ones of this type of computers. They could also be equivalent. It is two different ways to make it to the same place. And last but not least, we have this type of quantic algorithms, which are last generation, and what they want to do is to combine digital computers with quantic computers, taking into consideration that the quantic computers we have today have an evolution process to reduce the number of errors produced. For example, if we compare quantic current quantic computers and the digital computers at the beginning of the digital era, the quantic computers today have a technological maturity similar to the one of those first mainframes, first and second generation mainframes. So these machines we have here have some defects that are unequal results when they get warmed, and error correction. It is also very important and today in research of quantic research, and we will be resolving this as time goes by, because there is no reason to believe it is not possible to resolve it. It is a matter of creativity, talent, and investment, money, in order to build these error correction protocols, among others. And while that happens, a very important question that we need to ask about the world of quantic computing: what do we do to take full advantage of what already exists? Because the investment to build quantic computers is, in most of the cases, comes from the private initiative, companies such as IBM, Microsoft, and Google, etc. And there needs to be a justification in order to keep investing in those computers. And it is part of the answers that we have given to the scientific computers. We will be using the quantic computers we have today, and we're going to create a hybrid blended system with which we will be able to improve the results of the quantic computers through machine learning algorithms. And this is a type of algorithm that we have a variational quantic algorithms. There is a very important number of programming languages in order to simulate and to execute quantic algorithms produced by companies such as IBM, D-Wave, Microsoft. It also has a very important simulation and execution function for quantic algorithms. In other words, there is a wide range of platforms to work in with quantic computers. Now we will go to the core, to the flesh of this presentation, which is the application of quantic algorithms in cybersecurity. And this is going to be divided into two parts: threats against the cybersecurity systems and innovative solutions, the beneficial proposals of quantic computing, speaking about cybersecurity. The central topic The central topic of opportunities of development or challenges, or the threats against a quantum computer in the world of cybersecurity, is presented by this slide. What we have here, and during the 90s, in the last century, a U.S. mathematician, Peter Shaw, published a paper, and what he presented in that paper is that it was possible to resolve a mathematics problem, which is to find the period of a function, to do it faster using quantum computers instead of using digital computers. This is the contribution, the central contribution of the short algorithm. Now this algorithm that has been published, and something that refers to the calculation of the period of a function will have a close mathematical relationship with the factorization of whole numbers into prime numbers. Whole numbers can a prime or a compound. Remember, prime are the ones that can be divided by themselves and by one and to reach zero. And this type of prime numbers play a very important role in different cryptography protocols, RCA, for example, and it is also, and it will have an important participation in authentication processes and other cryptographic protocols. So on the one hand, we know that the cybersecurity systems today, several of them, will rely on the nature of the prime numbers, specifically. And this is what has to do with the next problem. I tell you, for example, give me the two prime numbers of number 21, 3 times 7. It is very easy. And the one for 15, the same, 3 times 5. But if I ask for the prime numbers and if we multiply, and they will produce 3,954,000, we will be able to do it, but it will take time. If that same request, if we request the same to a computer, the algorithms that exist today will need a long time to have an answer. And all numbers which are not prime can be expressed, but finding those numbers is what matters the most, is more difficult. The mathematical nature of prime numbers and several cryptographic existing models, digital computers will rely on that computing difficulty to find the prime numbers of a whole number in order to guarantee a certain level of complexity and security in those same protocols. If we do not have the prime factors and the compound number, we will be doing well, because until now no one knows how digital computers can resolve this factorization. And Professor Shore, he was a researcher at the AT&T labs. He came with his algorithm and the relationship between the calculation of time of factorization and the factorization of prime numbers and whole numbers. We could use the short algorithm in order to factorize whole numbers in a very short time window. In a polynomial time, it will be minutes or seconds or maybe hours. The short algorithm represents a threat, an opportunity, a challenge, an opportunity to improve in the world of cybersecurity. Someone could say, they're sure. So we are kind of safe. And the answer is yes. Yes, today we are safe, but the progress of the progress of hardware construction and the different refinements with the short algorithm allow us to see that in the next 10 or 15 years we could have quantum computers robust enough running the short algorithm so that it can be a lethal attack to cryptographic systems. We will now have a very important question for companies. What do I do? I do not have a problem today, but in 10 years do have a problem. So what can I do in order to protect my organization? And the answer is complex, but the most important part of that answer is to use algorithms of post-quantum cryptographic algorithms. And basically what it means is to replace the algorithms which are contained in the cybersecurity protocols, and what is depending on the complexity of factorizing whole numbers into prime numbers, and to then replace those algorithms for others, and consequently those are going to be immune to the attack of the short algorithm. And those algorithms are this. It's been hard, very hard. Standardization, certification, and standardization of these algorithms. This is work by NIST in the United States. Admirable work. And now we've been working with research centers. It is 5 or 6 post-quantum cryptographic that can be used to replace other protocols. This requires we need to identify in the company and wherever you work how we would like to make this process. For example, for companies which are doing hardware development or software, and it would be interesting to implement these protocols since the beginning. And for the organizations, it could be through companies that render computing services, and it could be a matter of making sure post-quantum protocols are included in order to guarantee the completeness and the data of the company. So there are different ways to protect the companies. And those who are responsible for these areas of communications and computing will be talking to vendors, or maybe into those who decide to implement this type of algorithms internally. Now, innovative solutions of quantum computing is distribution of keys. It has always been a difficult to resolve problem. There is no solution, safe solution in the classic physics. And the fundamental problem is that if I want to distribute a key from point A to point B, a set of A1s or zeros or characters that I will be using to cipher a message, if I want to apply a cryptography protocol that would allow the construction of a new text that no one else is going to be able to understand except those who have the corresponding key, there is communication channels, the phone number, smoke signs, telegraphic digital communications. They all have a problem. It is the fact that I can be a spy could be listening to what goes through a digital channel, and without others know that I am listening, and without others knowing that I am listening. And this is just an example. For example, if people are talking in an airplane, if two consultants are speaking about a client, this is a worse idea. Very poor practice of consulting, because those two people do not know if the one behind belongs to that company or if it is a competitor. So they will never know that others are listening. Why? Because information transmission in the world of classic physics is like that. We can listen to it without necessarily knowing. We can share it without necessarily knowing that someone who is not authorized is listening to that conversation. Quantum computing, on the other hand, in people, in those three, Charles Bennett and Gilles Brassa, and separately produced the first quantum cryptographic protocols, and we will have a likelihood of listening to a spy who is hanging to the network in order to steal information from the key with which we want to do cryptography. Charles Bennett and Jill, they created a protocol known as the BB84 protocol, Bennett Brassard, and they published it in 84. And Arturo Deckert was honored to, he was my mentor in Oxford. He invented this protocol in 91 with the same purpose, with a different mathematical structure, but with the same objective to create communication channels for the creation and distribution of keys better than the ones we have in digital computer. And in these channels, we will be able to identify with some likelihood that there is someone listening. Another example, and this is the end of my presentation, the use of quantum technology to counteract. This is a paper that I wrote with several colleagues of the Inter-American Development Bank and with Continuum. And what we basically did was to show how we could use quantum technology in order to protect blockchain systems. And as you know, the blockchain systems, blockchain is like an alloy of different protocols, cryptography protocols, and many of those protocols are subject, as I said, they rely on the difficulty of finding the prime numbers with the integer. In this paper, we show that it is possible to protect by adding one layer of hardware on blockchain, the systems and the data that could be at risk due to the type of protocols and cryptography and factorization of whole numbers into prime numbers. This paper is available in open access. If you want to download it, you can do so. Now, I want to quickly speak about the interaction between the hard part of research and computing, quantum computer and cybersecurity, and the different players in the internationally in the world ecosystem, those who are interested in knowing the progress of these disciplines, the limits, and how to integrate solutions and how to get defended, how to defend ourselves in the case of large companies, organizations, and governments. And today, medium-sized and small companies. I've been working with the World Economic Forum in recent years doing this analysis to know what is the possible impact of the quantum technology and cybersecurity, and what is the perception. What is the perception of the most important players, governments, and CEOs of very big companies on how to include quantum technology into their papers, how to protect data, how to use the short algorithm, how to use a post-quantum technology to use those new technologies to protect and to benefit organizations, and it can be profitable organizations, NGOs, and every type of organization created by human beings. And here we have several examples of papers, and I've been the co-author of most of them, and you can download them all from the website of the World Economic Forum. They are for free. There's this paper about the transition towards a safe economy using the quantum mechanics, and this paper, I love it. Out of all the ones that I have written, this is my preferred one because it is given the best practices, and it is a guidance for governments and organizations to be able to identify which are the parts of the cybersecurity systems that could be in danger and what to do in order to resolve that problem. And here we have several documents that can be interesting. And as I already told you, this is all available for free in the website of the World Economic Forum. 2 more minutes and that will be it. Quantum computing, as I said, it is an advanced technology where we find investors, global companies, small, large companies, and governments. And this, I am showing you this image because I want to show you one thing. Out of all those people which are celebrities in the world of quantum computing, the most famous one is Richard Feynman. And out of these eight researchers who are first and second generation parents of quantum computing, they are all alive and they are working on, except for Richard Feynman. Unfortunately, what do I mean by this? That the world of quantum computing is a very new world, super new, and where we can do lots of research, lots of findings. And for those who do research as a profession, it also means one way to bring bread, food to our tables, to build a professional career around the progress we can have. Speaking about communications, sensors, data processing using quantum computers. There are many, many things that we do not know today, and this is something that I wanted to underscore. 7 out of these 8 researchers are still alive and working, so it is a brand new discipline, and the founders are still in the labor market and they are making progress. So this is an invitation so that we can think about routes and new processes, new things we can build in this discipline. I would say that one of the most promising areas of quantum computing is cybersecurity, and cybersecurity is the intersection of all these disciplines with supercomputing, specifically GPUs and HPCs. These are some of the companies that have worked in this area: Microsoft, Continuum, Google, other companies which are smaller, but they are also working in this area. This is the end of my presentation. This is the end of my presentation. I only would like to very quickly share something about my research, which is the conventional computing lab. We've been working in all these areas. We do scientific engineering research, transfer to the industry, and new methods to teach quantum technologies, because as we saw, mathematics are different, but there is always a nice way or less effective way to show how quantum computing works. This is a photograph that I took. These are some courses that I teach in the United States every year. I hope that I will be able to do the same in the United States next year. And it's engineers who have been working for 25 years and they want to learn new things. This is um, this is the news about the first formal process of knowledge transfer process, and this is something we've done in Latin America. I was the leader of this project and in the transfer of knowledge of quantum computing for AstraZeneca. And here we have a set of things we've been doing in the group, different papers. This is another paper for the National Institute of Public Administration on Quantum Technology and Cybersecurity. You can download it, it is for free. Some books, and this is a Facebook website we have if you're interested in knowing the progress, ideas, and the works. It is very, very important. Speaking about quantum computing, there are different areas of quantum technology. If you want to subscribe, please do so. And this is the end, and we will now have questions and answers. The International Year of Sciences this year, as declared by UNESCO, and we're doing several things in order to celebrate this year. Conclusions. Please see this computer, the Timex Sinclair, was the very first computer that I used in my life when I was a child. With this, I wrote a very primitive version of Pac-Man, very, very primitive. And then, as years went by, the first computer, the first quantum computer I had access to, after my PhD course in Harvard, and it's quantic derived quantic computer. So here we have the time Ziegler Silox Z80, which is a CPU, a very basic CPU. This is what we had at that moment, and here we have one of the first quantic processors that were available in the market. The transition and the period between this computer, the Timex Sinclair, for me to program it and for me to program this quantic computer, it took me 25 years. And I am saying this because I know there are several students among you. So this transition to knowing different areas of the same discipline, it requires understanding different fields of mathematics and physics. So this took 25 years. What will we expect with the students, with those who are about to graduate or joining a college or something like this, but with asteroids, something very, very fast? Technology changes very quickly, and the question is what to do for not to be obsolete when technology changes this fast. And the answer, or at least my answer is go to the basics: hard mathematics, physics, computing, all the theoretical bases that would allow us to understand the world, regardless of the application or technology that we use to retrieve data. Mathematics, physics, and theoretical computing. This is the base of all the technological disciplines we have today. And to finish, quantic computers, like the data science systems and any other type of technology, can be built to get destroyed. Yes, and we can also build them to make this a better world where we all fit, regardless of our condition, regardless of our gender. Nothing matters except the well-being of our peers, scientists and engineers, those who build technology and do science. I am not saying that we should all follow the same paradigm. What I am saying is that when we use our knowledge to benefit mankind, we're gonna when we live, we're gonna leave this world better than the world we found. Thanks so much. Thanks for your attention, and I will be here to help you in case we have questions. Thanks, Salvador. Very amazing. Personally, I am an electronic engineer. This is my first career, and it's been very inspiring, very interesting what you said. And I would love to have your presentation. I know that in the documents, we have the links to the documents you mentioned. If not, we will research, and the video is going to be recorded, and we can also listen to you in the YouTube channel. I am Carlos Ramirez, and I am from Mexico. I have several questions, a very, very interesting presentation. I would like to first of all ask you, for those who are not mathematicians and for those who are not scientists or technologists, because here we have people from other disciplines, lawyers, politologists, economists, and for those in these other fields, how can we approach, how can we contribute, and how can we contribute to the development of quantum computing in countries like the ones of Latin America, apart from scientific and technological development by those who do this degree and those doing research? What about those who are not immersed in this? How can we contribute? This is the first question. The second question is, in Mexico, I understand that quantum computing is not within the national priorities. We have spoken about investments in supercomputers, and there are several projects of CONACYT, which is now the Ministry of Science and Technology, in order to utilize supercomputing, but I haven't heard anything about quantum computing, and I do not know if we are being left behind. And last but not least, which are the differences you see between the supercomputers and the quantum computing for those who are beginners? Thanks for your questions. The first question is the recommendation that I always make in order to identify how and it's possible to use quantum computing and in general terms the quantum technology for the benefit of organizations, many in the planet, in Latin America, and as well as to give explicit knowledge to the different areas of an organization, as you said, lawyers, the CEO, for example, the president of Romania is a mathematician, but that is he was a winner of a contest. That is one case, and most of the leaders of organizations have different backgrounds. My recommendation is to talk to a university, that is an expert with experts, and let's organize workshops. This is the best way, because information about quantum computing, there is a lot, and there is a complicated topic, which is the one of the hype, the exaggeration of the results. Every other day there is a breakthrough, and that is not true. It doesn't work like that. But we have such so lots of information that it wouldn't work. So we need to do transfer of knowledge between the academia and the industry. Because, look, the reason of minor hype is one, very easy, money, to bring more money and funds. But in the case, we are not saying no to money. No, of course we want money, but we want it differently. We are agnostic because we prefer one or another technology, and what we are looking for is to have a critical scenario to know what there is and how to apply it. So this is going to be my first answer. Olga, do we have time to answer more questions? Yes, only two more questions, 2 minutes. Thanks. I am Gabi Salazar. I am a lawyer, and my question is very easy. What is the role of ethics in the development of quantum computing? Thanks for the answer. It depends on what is the stage of the development of quantum computing we refer to. If we mean the process, the theoretical construction of protocols of algorithms, and the construction of hardware on which we will be running quantum algorithms, the ethics will do nothing, because it is purely engineering and scientific work. And ethics, of course, plays a very important role when we think in applications of quantum computing. And yes, there it is very important to have convergence of engineers, directors of companies, political leaders, and heads of a state, and lawyers, among others, in order to define the ethical framework on which we will be to use the quantum computing. I spoke about governance of quantum computing, and it touches this topic, how to use all these computers, quantum computers, in an ethical way. And we also have an organization, HESTA, in Switzerland, and they have the Open Quantum Institute. And here we frequently see topics such as ethics and quantum computing. So I would say that the topic of ethics, it becomes relevant when we think how to use all these technologies for this application. And of course, in this area, ethics and the study of it in the development of applications plays a very important role. One last question. Good morning. Congratulations, Salvador, for your presentation. My name is Stanley Vargas, and I come from the Dominican Republic, and I represent the Interior Ministry of Police. My question is, which are the main risks that quantum computing represents for the protection, the security of sensitive data, and how is this being addressed institutionally? And another question, are there regional or international initiatives that help Latin American governments to transition towards post-quantic algorithms. Thanks for the question. The answer is that in essence, or the danger, or the most important challenge, or the scenario, is the application of the Sure algorithm to do factorization of whole numbers, as I already told you, and to be able to break some parts of the protocols of cryptography as existing today. Maybe in 5 years from now, other things, but today this is the trend. Now, speaking about transition, yes, there are international efforts, the one by NIST, mainly in order to identify and to standardize and to certify post-quantic protocols. But that's it. But the transition of those mathematical definitions and post-quantic protocols to the industry is something to be addressed. And it depends on the maturity. It depends on the maturity of each one of the states, on the maturity of each sovereign state with regards to what it wants or what it doesn't want to do with this type of technologies and how to protect data of government and of organizations. And to answer another question, in the world of quantum computing, Mexican scientists have done a lot. If I may, I will very quickly present all this work. 30 seconds. This is an initiative, and in this website, dico.com.mx/imtc, you will find this document, the document of the Mexican Initiative for Quantic Initiatives, where we have regional work and national work by Mexican scientists. All this with la DICO, this is a branch of the Society of Physics. Now, speaking about the support of governments, it changes a lot. Because on the one hand, in Mexico, there is no initiative, there is no clear initiative. We have many of the components needed in order to create a national program for the development of quantic technology. We have human resources, but we do not have the money to do it. And this is one more topic. It's something that has to do with more with government. In the case of South America, I know that Argentina and Brazil mainly have a very robust structure. Brazil has a national initiative for the development of quantic technologies with money from government and from the private initiative. But I would say that in Latin America, the leader for the development of quantic technologies and the transition to the industry is Brazil. And we have in the case of Argentina. In Colombia, they also have something, but at the first place is Brazil. Thanks, Salvador. Very interesting, very inspiring. At least in my case, that I love mathematics. I really appreciate your time. Congratulations for your career, for your background, and for all the work you do. And we will be in touch with you via email. Thanks for your time.
Personalmente,
If you could share the presentation, I will appreciate if you could share the presentation.